Hi, in this video I'm going to do the last example from the Class 24 notes. In this example we're given some basic information about a thick lens model of the eye, and we're asked to find the correction necessary for this eye. So let's start by diagramming, making a figure for what this eye looks like. A cornea, and it makes a thick lens with the crystalline lens at the back, and then somewhere over here is the retina. It gives us some information about where the principal planes are. So H1 is 1 millimeter from the cornea, and H2 is 2 millimeters from the cornea. We also know, we're told that this eye has an equivalent power of 59 diopters, and of course a reminder that the N value here is 1.336. In trying to solve for what the correction lens is, our first step, as usual, as we would do even with our thin lens model of the eye, the first step is to think about where's the far point. So locate the far point. Now, what does that mean? That means it's the object location that the lens is able to form an image on the retina. And so we can apply our V equals U plus P. In this case, we're looking for the object far point divergence. So let's just rearrange this to solve for that. The far point object divergence is the image distance minus the power. Now, what are we going to use for the image divergence and the power? Power is the equivalent power of the focal length of the thick lens. Image divergence, so this is relative to H2, so this is going to tell us about this distance here. We have this additional piece of information that tells us that there's 21 millimeters from the cornea to the retina. From retina to the front edge of our thick lens is 21 millimeters. All right, well that means that we know what this distance is. The distance from H2 to the retina is just that corneal distance, cornea-retina distance, minus how far H2 is from the front surface, and H2 was 2 millimeters. Right? So VH2 looks like that must be 19 millimeters, 2 millimeters less than 21. All right, so now I can do my divergence equation down here and say that this is N over VH2 power, and so this is 1.336 over, and that is plus 11.3 diopters. So this is telling us the far point divergence, right? But we have to again remember, since this is a thick lens, it's a divergence relative to H1, the primary principal plane. So if we wanted to find out the distance, so little u far point, we have to remember that again this is going to be N over the divergence. For object side, on the object side of our thick lens, the index of refraction is 1, so we don't have to really worry about that. 1 over 11.3, this is 8.85 centimeters. But, again, we have to remember that distance is measured from H1. Also, I notice that this distance is positive. The object divergence was positive. What is that telling us? It means that the direction that the far point is from the principal plane is in the positive, in the direction light is traveling, and so it's a far point down here, and so that's a hyperope, right? This is a far point associated with a hyperope, and that should be expected when we see that the far point divergence is positive. That's associated with a hyperope. Okay, so what we've done now is we've located where the far point is relative to the eye, relative to the primary principal plane, right? But then we could get it from anywhere else. It might be interesting to think about, so before we think about the spectacle lens, let's just think about what the contact lens correction would be. And from the thin lens experience, we would have said that the contact lens, the power the contact lens needed to correct this patient would simply be the far point divergence. But here you can see that can't be true anymore, because if we put a contact lens right at the front of the eye, the way we should think about it is the job of the correction lens is to take parallel light coming in and form an image at the far point, right? So the job of any correction lens is to take parallel light coming in and form an image on the far point. In this case, since it's a hyperope, it has to form an image at some location, right? The far point somewhere downstream. And so when it does that, right, remember that means that this distance from the lens to the far point has to be the focal length of the contact. And if we look at our picture up here, the required focal length is the distance from the lens all the way over to the far point, which is way over here, right? That is not just equal to this far point distance that we calculated here, because there's this extra little piece here between the front of the lens and where the principal plane sits. So the required correction focal length would be the far point distance plus our H1 here is 1 millimeter away from the front of the lens, so plus 1 millimeter. So that would be 8.95 centimeters. And so that would correspond to a power. Okay, so that would be the contact lens correction. Now we can turn to spectacle lens correction. And since we've worked out how the contact lens correction, you can probably see how the spectacle lens correction is going to go. It's basically exactly the same idea. Number one, the job of the spectacle lens is exactly the same. It needs to take parallel light coming in and form an image at the far point. The difference, of course, is that our spectacle lens is now some distance. So we'll call this PC, and this is spectacle, and the spectacle is some distance. Nonetheless, it works just like the contact lens, which is that the distance from the spectacle lens to the far point needs to be the focal length of the spectacle lens in order to accomplish this, right? In order to form an image at the far point with parallel light coming in. So we just have to look at this figure to read off what the focal length of the spectacle lens needs to be. It needs to be this distance here, right? The distance from the principal plane to the far point, the 8.85, plus a little bit of how far H1 is from the front of the lens. I think that was 1 millimeters, and then plus the vertex distance, how far the spectacle lens is from the front of the lens. So if we add all those things up, the focal length of the spectacle lens needs to be the far point distance plus, let's see, 1 millimeter to get from H1 to the front of the lens, and then 10 millimeters of vertex distance. So this is 8.85 centimeters plus 1.1 centimeters of additional amount, and so that gives us 9.95 centimeters. And so then the power of the spectacle lens is going to be 1 over that, plus 10. So you see from doing these examples that finding the correction power, whether it's contact lens or spectacle lens, follows the same basic idea that we used previously when we had a thin lens model of the eye, which is that we require our correction lens to form an image at the far point. So we've got to find out where the far point is, and then we use diagrams like this to work out what the necessary focal length, in other words, how far is the lens from the far point. That serves as the focal length, and then we can invert that to find the power of the required correction lens. So it's pretty much just like you're used to doing. It's a little bit more complicated just because many of our distances that we calculate from our v equals u plus p are actually from the principal plane, so we have to take that into account.